Hello to everyone on Zoom. Just bear with us 1 minute. Getting started here shortly. Does anyone know what is going on outside, like here?
I was gonna ask you, I was like, I think you're just waiting for. Yeah.
Oh, exam.
Yeah.
Okay.
Why else would be somebody who?
Exams now? Yeah,
It looked like somebody was handing something out the front door.
they know what it was. It's too much that was
Yeah,
going on.
I had to use my, deep voice to get through.
I've heard someone like talking about not having phones.
Yeah.
Uh-huh.
Problem.
Okay. Okay, that is perfect. Did anyone watch the Apple series for the?
Oh, yeah.
Yeah.
Yeah,
did you
changed
do?
mine.
Oh, really?
I have the 14 Pro Max.
Oh,
So
okay.
I have to change it. All the specs and everything, it's about time they change
It's
a
about
lot
time.
of stuff.
Yeah, yeah.
Like they changed a lot. Most people that say, oh, they didn't change, no, this time they didn't. They changed a lot.
Okay. Yeah, I was watching it and I read something like with regarding their stock market, I think. Did it
Mhm.
drop?
Mhm.
Yeah, it did.
Yeah.
I don't know, but
It go up on Friday because
is Friday the pre-release? Okay.
my select.
Okay. Which color did you get?
I'm getting orange. I have to.
The orange one?
I'm just looking for a case on it, but it's gonna look dope though still.
I see. I see. No, the one cool thing is about their AirPods is that it's gonna be it has translation.
So that's the funny thing. So if you watch, so the thing is, don't go out and buy it if you already have the Pros 2 and 3. Don't buy it.
Oh, they'll just add it
They're
on?
just gonna add it on. The
Oh.
software is gonna be delivered into it. So you
Oh, okay.
don't go out and spend another $250 if you don't have to.
Mm-hmm. Yeah, I mean, usually it's just the battery hour time that's
Yeah.
gonna be increased.
Yeah, the battery time has increased, and then they also made the noise cancellation 4 times stronger.
Okay.
Yeah.
Okay, let's go ahead and get started on Zoom. If you can give me a thumbs up that you can hear me, that'd be great. Were they hearing our conversation? Okay. Thank you, Landon and Dion. Okay, so a few course logistics before we dive into our module is that our last TA, I mean, he finally got access to web course and his office hours is updated. So each one of them has 2 sessions per week. Guru has Thursday and Friday from 9 to 10, and Sirikar is Tuesdays and Thursdays from 4 to 5. So same way you join the lecture, you can join them. You can also join my office hours, which is included in the syllabus. So that is regarding office hours. So far, where we at in terms of the modules, we're currently in week 4. We gave last lecture introduction to Wireshark installation, and we did a simple lab. We spoke about HTTP. We finished it off last lecture. We got into cookies, and we stopped at web caches. So today our plan is to finish those web caches, and then we'll move on to our next. You could say our next mini module of the application layer, which will be email, SMTP, and the DNS. Okay, so that is for that. For the students that did not get a chance to read the announcement for the Wireshark has been adjusted, and also the deadline has been extended since there was a revision that needed to be done. But to go over it a little bit, I have referred here the Wireshark setup and basics if you haven't installed it yet. And on the specific lecture, we did the installation, so that's for you to go back and watch. The questions kind of remained the same. It's just that the websites have changed, and the specific details of the questions might have been tweaked a little bit. So for question 1, you have optional of 2 websites. You don't have to do both. You just do one of them is sufficient. And the reason I gave both is just to give you a diversity of both websites, and you can do either or. This one here is a German online archive and a database. And the other one is like a banking site, which is used for training and teaching about web applications. So those are for you to choose. Just specify which website that you're doing for question 1 and answer the questions. And here, funny enough that your IP address might be changed based on what website you do. Typically, when we tested it, the legacy website, it usually takes your IP version 6, and that all depends on obviously your operating system, your PC, and the browser that you're using. So it could be different, but it does not really matter. There's no specific instructions regarding the IP. If it's version 6 or 4, just specify it. Also, within the report, make sure it's the .pdf. That's the only file we accept. And write the steps to your answer and include some visualization as we discussed before. So now going back to our slides. We have discussed HTTP, the response status codes. And then here we talked about cookies a little bit and what cookies are. I can enlarge this. Oh, I have to share my screen to Zoom as well. Let me share my screen. Share it, share, yes, and it is recording. Okay. Yeah, just a recap of what we spoke about in the last lecture. We talked about cookies, and we know that the client can have multiple cookies from different domains. Here we have an example with eBay. So if we finish, we know that the client can have multiple domains of cookies, and an ID gets created for those set of cookies, and they get stored on the backend database, such that if you access the same website a week later, that specific cookie is used, and that is used for shopping, personalization, and stuff like that. We talked about comments here, and now is when we're going to pick up, which is web caches, also known as web proxy servers. So the idea of web caches is to satisfy the client without involving the original receiver. So we have a client, 2 clients here, and we have the origin server, and we have the proxy server in the middle. When a request comes from the client, if it's stored on the proxy server, then it goes back to the client. This reduces the overhead of going to the origin server. If it's not in the proxy server, then the request gets sent to the origin server. The response will be sent back to the proxy server, and it stores a copy of it, such that the next user, when they request that specific page, it goes back directly to them. So it's more efficient when requesting the objects, and it can be a very quick process. And keep in mind, proxy servers, they can be used with persistent and non-persistent HTTP connections. So here the idea is basically what we try and understand from this slide is that the web cache can be both a server and a client. It is a server for the original requesting client because it delivers the content directly to them, and it can also act as a client when it doesn't have that specific object inside the proxy server, so it goes back and requests it from the original server. So it does great things for us, such as it reduces response time, it reduces traffic as well, and it allows the process to be more efficient. So I think this is exactly where we left off last lecture, and we're just trying to talk about the performance of web caches in comparison to having access links. And here we have an example. Looking at the scenario, we have institutional network in the bottom with 3 local devices. We have an access link, we have the public internet, and the origin servers. So here the access link is 1.4 megabits per second, and the runtime trip is round to server is 2 seconds. And now we have each object is about 100 kilobytes in size, and the browser that are requesting at an average rate of 15 per second. So that means the total data rate going towards the browser is 1.50 megabits per second. So in terms of performance here, we have the LAN utilization is very small. 0.0015. And the local network is not the bottleneck here. The access link utilization is extremely high at 0.97. And this means that the access link is almost saturated. When we see here, when the utilization gets high, we see larger delays. The end-to-end delay can be broken down as the internet delay, the access link delay, and plus the LAN or local delay. So in this case, it equals 2 seconds plus 2 minutes plus microseconds, showing that the biggest delay is caused by the saturated access link. So the key problem here is that we have a high utilization of the access link, so the delay increases. So now we are trying to think on how we can improve the performance of this, right? And we said that one option is to buy a faster link. The access link utilization is the average data rate over the access link rate. So one option is to reduce the delays, is to upgrade the access link, but that could be very costly. So in this example that we see here, the access link has increased from 1.54 to 154. So the round time to the server, the object and the requests remain the same as we see in the top of the slide. With the faster link, the utilization still remains the same. Access link utilization drops from 97 to 0.0097. That means the access link is no longer congested and the delays are very low. So end-to-end delay as the solution of buying a faster access link is just going to be 2 seconds plus milliseconds and then a little bit of microseconds instead of minutes. The main drawback about this option is buying the access link, which could be very costly, but it is an effective solution in comparison to the one that we had before. Here's where web caches come into hand and how they are beneficial to us. To reduce the delays, what we can do is we can install a web cache locally within the institutional network, such that here the access link rate, runtime trip, also the object size and request rate are the same as the previous scenario. Nothing have changed. We want to know what will be the performance. If we go right here. Okay, just finishing up the slide and we will talk about what will the performance be. Which is actually in this slide. So we want to calculate the impact of having a web cache. Obviously, we said that local web caches are very useful because they state they have a sort of state of remembering the objects that were requested by the local users, such that we have an institutional of many users and let's say a company that usually has a limitation of what sort of objects they request and what certain things that they have access. So even if a new user requests something else, such that it goes to the origin server, when it gets sent back, the local web cache will have a copy of it. And usually the institutional is responsible for setting up the local web caches for their institution or for their infrastructure. So here we have a scenario saying that suppose the cache hit rate is 0.4, meaning that 40 of the requests are satisfied by the local cache and 60% go to the original server. So that means only 60 requests are using the access link. And here we have the data rate across the link, which drops to 0.9 because we multiply the 0.6 times the 1.50 megabits. So that's much lower than the 0.97 utilization we saw without caching. So that is one thing for the access link. Now, when we speak about the average end delay, we said that 60 of requests take the internet path, which is about 2 seconds delay, and 40% are satisfied with milliseconds because those are stored on the local web cache. So on the average delay, if we do the math for it here, is we have 0.6 multiplied by the 2.01 plus the 0.4 milliseconds, which gives us a result of 1.2 seconds. So the key point here is that the web caches is the best option for us. It is the most cost efficient option also for us. So we can neglect the option of buying an access link such that local web cache achieves the same utilization and performance without having as this much cost. So it is cheaper and the delay is lower than 154 megabits per second that we have with the upgraded link. Here's a conditional get because we have web caches and we know that they do store local objects. So a conditional get is basically, you can think of it as an if statement. So let's just start with a brief reminder of what get is. It's one of the request variations of HTTP. So it's a most common method. It tells the server, hey, send me this source, such as a web page, could be an image or a video. So when you go on Google, your browser, on Google Chrome, for example, and you're requesting the UCF, you are using the get command. So by default, every get request retrieves the entire object from the server, even if nothing has changed since the last time it was downloaded. Now, when we speak about caching, our discussion comes that the main challenge is keeping the cache up to date with the content that we do have. So that brings us the conditional get. And basically here is the conditional get as an overview is simply saying, do not send the object if the cache already has the most recent version. There is no reason for us to update the cache with the latest or the most recent object if we already have this object. So it helps us avoid unnecessary transmissions, it reduces delays and lower links utilization. Here's how it works. So we have a client and a server, and the cache includes a special header and the HTTP request. So it modified since date, as you can see here on the top. This cache is saying to the server, only send me the object if it has been modified since this specific date. So say you're accessing a web page, you set a specific date saying that if the page has been modified since that date, then I do want the new object or the new link. On the server side, what usually tends to happen is if the object has not been modified since the date, the server replies with a status code of 304 saying that, hey, it has not been modified. And it gives that object back to the user. So the cache keeps a copy of the date as well of every object that we do have in the local cache. So when it's not modified, it just gives that status code of 304 that we have here. To give you another example, if the object has been modified and in the local cache, the date has been modified, then we get a request of 200 OK, meaning that the server is going to reply and send the updated object. So this is the idea, such that if an object has not been touched or altered within a specific date, then we don't need to make a headache and request it from the original server, since that the local cache has a copy of it. So in summary, conditional gets, what they help us with is they keep content fresh without downloading duplicates, and it saves bandwidth and reducing delays. Now we spoke about HTTP1, and we said that with HTTP, there's persistent and non-persistent. We also spoke about HTTP, which is the vanilla or the plain version of TCP that does not have any security enhancement added to it. And we said that with the websites nowadays, we see it has an S at the end, which has the TLS security enhanced. So here we're going to talk about a little bit about HTTP2 to wrap up HTTP in general, because so far we talked about the applications, we talked about the HTTP protocols, and we talked about the variations of GET message. We took a look example of the request message, also the response message. We talked about persistent and non-persistent. We talked about cookies. We talked about web caches. So here, HTTP2 that we have here has additional enhancements to improve the user experience. And the key goal of HTTP2 is to decrease the delay when handling multi-objects requests. So HTTP was standardized in 2015 using the RFC 7540, I think, which is the code that is kept by the blueprint. We don't really worry a lot about the code, but we just want to take a look and see what the enhancement is. So compared to HTTP 1, it keeps the same things, like the method, the status code, and most headers field remain unchanged. Those will not be altered. The big difference is how the server sends the objects. And what it does here is it uses transmission order, which is more flexible instead of always being on first come, first serve objects. And I have an example in the next slide that helps depict this. So the server can also push objects that the client did not explicitly request. For example, pushing a CCC or a JavaScript file along with the HTML page is not really necessary, or it's not really the priority of what the client is wanting. So what happens with HTTP2, objects are divided into frames, such that frames can be scheduled to reduce the head of line, also known as HOL, and which is a common cause of delays in HTTP1. So the idea is that we want to send objects more efficiently without sending unnecessary things that are related to the object. So they do that by a transmission order. So it gives the server more flexibility to send the data efficiently, and it improves the page load times for clients. And here we have an idea. So in HTTP1, we have a client and a server, and here we have a GET request. So in HTTP1, requests are handled by the order they are received. So first come, first serve, regardless of what object they requested. Whatever you request first usually tends to get back to you first. This can cause the HOL that we spoke about, head of line blocking, which is one of the delays. So in this example here, the client requests 4 objects, as we can see here, O1, O2, O3, and O4, okay? And here, by looking at this figure, O1 is very big, it is very large, as highlighted in blue. Then O2 or O3 or O4, they're stuck until waiting for O1 to get delivered. This is inefficient because smaller object can have been sent out very much faster, but because they are blocked by the order of what comes first goes out first. And HTTP addresses this exact problem, where it splits into smaller frames, allowing the server to interleave them. So we can break the requests that are getting sent into frames, and we can maybe send out the smaller ones first, and then we can have the most or the heavy delayed objects get sent in also in an efficient way, but so it provides more of a balance. So that is the idea. So here we're going to have an example of how do we avoid the HOL blocking with HTTP.2. So we still have 4 requests that get 0, 01, 02, and 03, and 04. And the client is requesting something from the server, as we have an example here. What we do here is we divide them into smaller frames rather than a big block. The frames can be interleaved, which sent from the server to the client. And looking at the diagram here, such that the O1, which is very large, it blocks everything behind it as we've seen in HTTP.1. But when we break it into smaller frames and mix it with the other requests that we have, the result is that the smaller objects arrive much faster to the client. And then this idea demonstrates what HTTP.2 is powerful of and why they did an advancement from HTTP 1 to 2. So HTTP, as a reminder, HTTP 1.1 is that small files get stuck waiting behind big files. HTTP came and said, hey, big files, what we'll do to them is we'll chop them into smaller pieces and we'll send and we'll mix them with other smaller files such that the smaller files will get delivered quickly and the big files finish a little bit later, but nobody is blocked. So this is the idea. But in terms of the request and the response message, it remains the same. Like the body, the header lines, and all that stuff. Now, as you might know, we have HTTP 2 to 3. And it's also the same. It's also to reduce the delays in multi-requested objects. So in HTTP 2, it uses a single TCP connection to handle the multiple stream with the help of head of line blocking. It also creates some challenges. One of the limitations of HTTP.2 is the packet loss, because it multiplexes all streams into one TCP connection, such that if the packet is lost, recovery stalls all the other object transmissions. So even if we divide the objects into many frames and one of those many frames get lost, it has to wait for it such that it can recover. So the second limitation also is security. HTTP itself does not add security. It relies on being run by the TLS encryption. And we know over in the vanilla TCP, there is no built-in connection. So that brings us to HTTP.3 or 3 per se. It is built on UDP instead of TCP. And also it solves the problem of packets that get lost within the object transmissions that gets happen in HTTP.2. So what it does is that first thing it does is it's built on UDP instead of TCP. The next thing it solves is also security as per object error control and congestion control, such that there will be an allocated time for the frames of each object to get sent back to the client. Also allows a more efficient and a smoother pipeline of requests and responses that reduces also stalling. And we will talk more about HTTP 3 in the transport layer, but this is just to give you an idea. Since we're talking about HTTP, we might as well just cover it now to give you an idea of it. So that's a wrap for HTTP. We did a little bit of hands-on and we talked about it in specific. We know it's a stateless protocol, but persistent by two things, by the cookies that are getting remembered by the user, and the caching that extends its functionality. We also talked about non-persistent, which requires multiple connections. So if a website has 10 objects, we're going to need 10 different requests for each object. Also, we have to keep a track of everything is basically time. So the round trip time is going to be for every object with the non-persistent. Persistent came and reduced the overhead such that it keeps the connection open and it closes it based on a set idle time. If nothing happens within this time, then the connection gets closed. We said that cookies enable state management. They're very useful, but there could be privacy implications of them. Also web caches, how they came around and helped us such that we don't have to request from the original server. We can have a local web cache, and it also reduces the delay and the network load. Now, we talked about HTTP and the involvement of it. HTTP 1.1 brought persistent connections. 2 came out and added multiplexing and reduced the head of line blocking by breaking the objects into smaller frames. and 3 came out and use UDP for faster and more security, for more secure and delivery. So this is typically what it is, and you can say in computer science and in the evolving of technology. There's a new let's say protocols that comes out, and there's also limitations with them, and we need to improve those such that we go and test. You can think of the idea of doing research. When you start doing research, you have to read a little bit about what domain you want to study, what is the problems in this domain, and you study the most recent ones that came out maybe in 24, 23, 25. And then you go say, hey, oh, maybe I can improve on this. Oh, let me test this and see if if it could work. So that is the idea of HTTP. So that is a wrap of HTTP. Next, what we will move on to is our next topic, which is going to be about, give me 1 second here. Which is about SMT, the email protocol and the DNS. So we can close this. Let me just share my screen. Okay, I have a cool activity to start this and to give you an idea of, as we dive into the, to talk about IMAP and SMTP. So for the objective of this, we're still in the application layer, but we are going to talk about DNS and SMTP. We want to explain the main components of email systems, user agents, mail service, and how typically emails, we use emails every day. We get an email from someone and we respond to it, but we want to know how that works. We'll describe the transfer messages and compare it with HTTP, recognize the different protocols that do come. We'll talk about DNS, which is the host names. If you go on your CMD and you type in ipconfig, or when you ping something, you see that whatever you ping has a DNS, which is basically the phone book for networking. It keeps track of the domain name and the IP address. And we'll talk about how it's hierarchical, and we'll trace the process of DNS through the root, TLD, and other authoritative servers. So as just a statement as usual, the class is recorded and the ample portion of the slides are derived from the book. So this is where we are in the application layer so far. We covered HTTP lastly. Next, we'll move to emails. Okay, and we'll see how SMTP works and IMAP works as well. So this is just for us to go ahead and mess with a little bit, is assuming that you receive an email like this, and we do receive a lot of phishing emails. We look into like a lot of details of it, such as the headers, the sender that is sending, what's his source, and the intels. Can we tell, or can we specify how we can tell an email is phishing or not based on this? Here we have an idea of something that came from Google, and it has my name at the bottom, and it says, congratulations, you want a free Google Pixel 7. Here's the invitation link. And it looks legit. It has the day and time. But what are I would say, what are the characteristics that we can use to spot that the email is phishing? Yeah.
Free piece of something, bro.
Yeah, obviously, right? Nothing is free in today's world. We wish it was like this, but rarely it's not. So be aware to everything that is free. It might not be true, right?
Nothing's free.
Nothing's free. Go ahead.
You can also say the email, if you look at that pixel giveaway at Google.
Yeah, you look at the email,
Mm.
the source of the sender, and you want to see, is this credible? Is it known or not? So yeah, so we can all agree that this email is not real. It's phishing, correct?
Mhm.
And here's for several reasons. As you mentioned, the first thing is they made their email address appears that it was sent from Google by changing the sender name. That is a very cool thing, but we will not get into it in this lecture, and I don't think we will cover it. We were just talking about the main protocol of emailing. This is like the cool side of emailing, I think. So we will not cover that specifically, but I just want to give you a cool activity to as we get into this. Also, as you said, be aware when the offer sounds too good to be true. And also here, when we click on this highlighted link, before we click on it, we can see a lot of things. Is it HTTP with S? Is it has TLS encryption or not? So the access to share your access to your accounts. So this seems like it's not credible, and it is phishing. So now we are getting to the email, and with emails, we got to keep three major components that we have to talk about. So the first thing is user agents that we have, and the user agents are us. Give me one moment. Tiago was talking about, in this case, was it sent from the Google domain? Did the mark certification fail? What happened? And this is maybe a good question for you guys to think of. Was it sent from the Google domain, or what exactly has happened such that the source has been tweaked? Does anyone have an idea? So yes, yes, Tiago, and in the essence, yes, it got tweaked and it was sent from the Google domain. Regarding the details of that, there's a lot of details that go into it. So and it's not something that we are going to cover. We're just going to talk about the main protocol and with typical emails, how it works from a sender and receiver. And it's if you can think of it's a client to server modular architecture. But I think this is one interesting thing is how we can see how our phishers or malicious intent do something like this. So while this is an interesting niche of SMTP and emailing, the main objective of this lecture will be about typical emailing. So back to a little bit to the slides, we have the user agents, that is us, the mail servers is the typical service, and the SMTP is the protocol. And we said that protocol is just a means of communications. For the web, we have HTTP and all that. So now a little bit to talk to you about the user agents. This lets us, we edit the message, compose it, send it, and read it. An example of that could be your Apple Mail, your Outlook, your email phone on the app. So messages are both incoming or going, and they are stored on the mail server, but the user agent is what the user interacts with. So on the right figure here, we see that each computer represents a user agent, and each server box is a mail server, which stores the ongoing messages highlighted in green, and the user mailbox highlighted in yellow. And then finally, the communication happens using the SMTP protocol. That's what the red arrows represent. And finally, the recipient, the mail server places the message into their mailbox, and the user agent finally retrieves it. So as you can see, it's very close to a client-server architecture. The agent acts like the client, and the mail server acts as the server to process and store the messages. No, so let's look more into the mail servers a little bit. So a mail server performs two key functions. It holds the mailbox that are highlighted in yellow, and that contains incoming messages of each user. And it also keeps a message queue, shows in green, that stores the outgoing messages waiting to be sent. So when one user sends an email, their server, what typically does, places that message in the queue, which is highlighted in green. From there, it is transferred to the mail server using the SMTP. And the SMTP protocol is what allows us to exchange those messages between the user agent, and the mail server. So here we have an example of the typical Alice and Bob. And let's say they do want to send an email to each other. So here we have on the left, the user agent. We have two user agents to be specific. We have Alice and Bob, and they are going to communicate with each other. So Alice on the left here wants to send an email to Bob, shown on the right. So both Alice and Bob have their both user agents. These could be their typical Outlook or Gmails, and they both have their own mail server, right? So what happens in step one is that first Alice uses her user agent to write an email, and when she finishes writing it, she hits send. What happens in step two, once Alice sends the message from her user agent, it goes to the mail server, and at this point, the message is placed to be onto the ongoing to be sent on Alice server. Step three, what happens is next Alice mail server needs to deliver the message to Bob's mail server. So next we use the SMTP. Alice server, what happens is they open a connection, a TCP connection to be specific, because we don't want the entails or the information on the email to be sniffed. So over the TCP connection, Alice server is acting as the client that transfers the message to Bob's server. And in step five that we have here, Bob's mail server, what happens is receives the message and places it into Bob's mailbox, where it's stored until Bob checks his mail. And then finally, the last thing is you come and check your email. Bob comes and opens his user agent, or retrieves the message from the mailbox, and Bob can read the message that is coming from Alice. So this is the idea of it. And to give you an analogy is that you live in Florida and you have someone maybe that lives in Miami. So what you do is you go to your mail server, which is your mail outside your house. You put whatever you want to ship or the letter, and then it gets stored on your server. Then the postman, could be any companies, FedEx, comes and takes it from the server, transports it all the way to the destination, wherever that is, and it gets stored in the mailbox till the agent comes out, or the person that is supposed to retrieve the item, and takes it out. So here, talking more about the official specification for email transfer, and we must state those in every protocol. Here it's the 5321. It describes how SMTP works in detail. Okay. So the first thing is it uses also port 25, and when it sends a message or initiates a message, it opens a TCP connection to the server. And this process is a three-way phase process. First thing is a handshake is being happened, like with the greetings, also transfer messages, and the closure of the connection once everything has been done. So SMTP is usually like HTTP. It has a request and a response, but here we are sending and receiving. So the commands are sent out in ASCII text. The server replies with the status code and a short phrase. And sometimes you guys have tried, right? When you send an email and you put the email that you specify, after you send it, you get a response code saying that your email has not been delivered, right? Because we messed up maybe with the domain. So that usually happens as well. So here in this figure we have here on the right, we have the SMTP server is the client, and the server is the SMTP server. First thing, the initiation. Here's how the handshake happens. Initiation of the TCP connection opens first with the server. After the connection established, we see the handshake reply with a status code of 220, saying that the service is ready, and sends the client hello. Then the server replies with 250 status code saying also hello. And then after the transfer, what happens is that the eventually closes, as we see in typical HTTP request. So that is the idea of it, of emailing. So now we look a little bit at the session that happens between the client and the server, and we did this also for the HTTP. So here's one thing you need to be aware of. We have a letter S. This is for the server, and C is for the client. And we have an example here that the server of 200 hamburger.edu wants to send a message to alicekrebs.fr. So there's also there's edu emails. We will get into that in a little bit. But for the first thing that it does, hamburger starts with a greeting saying greeting 220 with the client. The client responds with hello Krebs. The server acknowledges that request and says, hello, pleasure to meet you. Then next what we do is identify the sender and receiver. The mail is coming from Alice at Krebs, as we see here in line 4, and the server replies with sender OK. After that, the message transfer happens. The client signals that it wants to send the message with the body of data, and the server here responds with the code 354, says enter mail, and with on a line by itself. So here it says, do you like ketchup? How about the pickles? That is the data or the body of the email. The client ends up the body by typing a single period on the line. That's an indicator that it is at the end of the data line. So the server replies back to them saying, oh, 250 message has been accepted. And these are the status codes similar to HTTP, such that when we see 304 could be moved to a permanent another location. So these are similar. So the client after that quits, and the server replies with the closing connections. So a little bit of observations about SMTP and how we can compare it to HTTP. First, we want to look at the data flow. HTTP is a pull-based. The client requests an object, and the server usually responds back to it. SMTP is a push-based. So the sender, the sending server actively pushes the message to the receiving server. And both protocols here are using ASCII command response interactions, and they do both have status codes, but they are different when we compare them. In HTTP, if we talk a little bit more, each object is encapsulated in its own way. In SMTP, multiple objects like attachments are bundled together as a multi-part message that we have. And also on the specific side of SMTP, it uses persistent connections. So the TCP stays open, that we saw in the previous example with the hamburger website and also the Alice Krebs. So it does stay open. Also to keep in mind that SMTP requires the header and the body. Those are crucial, and they must be encoded in 7-bit ASCII. That's why special encoders are needed for attachments. Like PDFs or images, and the CRLF is to determine the end of the message. And we saw that with HTTP as well. That's an indicator, that's an end of the message. So here, just to give you a visualization about SMTP that moves email messages between servers. And here, this is talking about the format. And this specific RFC 2822, it is the standard syntax for an email message. It talks about, hey, this is how the message should be. And this is what we have here. So an email has two main parts. It has the header that contains to, from, and subject. And we also have the body. This is the actual message of the content. And the diagram on the right shows here is the structure. We have our header, and we have a blank line, and then the body of the message starts. So this is a format that is set such that all emailing or all the SMTP protocol follows the same structure. We know that the header begins, there's a blank line, and the body starts. So up to now, we only spoke about how the SMTP delivers and store messages from the sender receiver, the sender server to the receiver server. But we want to now talk about once the message reaches the receiver server, how does the end user actually retrieve it? So when Bob sent a message to, or Alice sent a message to Bob, we said that it gets stored on Bob's server, but how does it get pushed to Bob? So we know that SMTP is only used to store, is only used for delivery and storage only. That's why we use IMAP. And this is another internet mail access protocol. With this protocol, we know that the mail is on the server, and the user can retrieve, delete, or organize this into folders while the data stays on the actual server. This is what allows such that when we go and type a message but we don't send it out, when we go to our email, it is saved in the draft, and it's also the same. It does not get changed. Also, another common way is the HTTP-based webmail, and this is we have services like Gmail, Hotmail, Yahoo, which I don't think anyone uses Yahoo anymore, right?
No.
No. Okay, that's good. So looking at the figure here, Alice, the user agent, sends a message via SMTP to her mail server, and the message is transferred between the mail servers again, from the sender mail server to the receiver mail server. And then finally, Bob retrieves the message from the server using the mail access protocol that we talked about, either AMAP or HTTP. So that's how it makes its full journey from a sender to receiver. So basically, that is the idea of SMTP. We said that SMTP is just to send and store. We use IMAP is to basically push out the content or the email to the receiver. So next we will talk about the DNS, and this is like the internet phone book. It gives us the IP alongside with the domain name system, such that UCF has a specific IP, and it also has a domain name, which is ucf.edu. So let's take a closer look on how they work. So what is the domain name system? It's just like people can have a lot of identifiers. We also have identifiers. You might have your specific UCF ID, you have your social security number, your name, your passport number. These are our info that classify to you, that are personal to you. So when it comes to internet hosts and routers, this is a 30-bit used to address datagrams. And here we have is like another identifier, or a human readable identifier, is cs.ucf.edu, that is used by humans. It is neat in a way that we can just type that and it directly takes us to that. So the challenge is how do we map between names and IP addresses in both directions? So the way we do that is the domain name system. It's a database usually, and it's organized in a hierarchy of many name servers. And the application layer protocols enables host and name servers to communicate with each other to resolve the names into IPs. And we will dive more into it. So the DNS is the core internet function, but it's implemented as an application layer protocol. And because of that, we are working with host names, so it is related to the application layer protocol. This design of the DNS can have a complexity when it comes to the edge of the network, where hosts and servers interact with each other instead of being buried in the network core. So let's speak about a little bit more about DNS. We know that DNS provides several important things. That host name to IP translation. This is where allow us to type UCF instead of the numeric IP address for the UCF domain system. Also, a host might have it cannot canonical name, but also has several aliases names. So it helps us also map those aliases names to the same host. Mail server aliasing is DNS is also used for the mail server, so that the email can be properly routed. Also helps us with load distribution for popular websites that are often replicated servers. So DNS can return different IP addresses to the same, for example, host names or across multiple servers. So the question is why should we have a decentralized DNS? Why can't we just have one centralized DNS? And the idea is that it's not very simple to have one big DNS server for the whole internet. As we said, the internet structure is very big. It starts out from devices, it goes to switches and routers, and it grows very big. It goes regional and global. So the centralized DNS does not scale. So this is the problem, and it gives you a sense of how massive DNS traffic and why it must be distributed in a way. So this is the idea of hierarchy that will come into play when we speak about DNS. So a hierarchical database that you can think of is distributed in a way, and at the very top we have the root DNS servers. And those servers don't store every mapping themselves, but they can direct to top level domains. So we can have .com, obviously, such as Yahoo or Amazon. We can have .org. We can also have .edu, .ucf, or nyu.edu. So it starts from the root, then it starts simplifying to these other servers that we have. And then finally at the bottom, we have the authoritative DNS servers as well. Those are responsible to store the actual mapping between the host names and IPs for a specific domain. So for example, like here we have Amazon. The authoritative server for Amazon can return the IP address for Amazon itself. So let's just talk about an example. Suppose a client wants the IP address for Amazon.com. First, the client queries the root DNS server, which responds with a .com server because we are requesting Amazon. It falls under the .com DNS servers. Then the client queries that DNS server, which provides the authoritative Amazon DNS server. And then the client queries which returns the IP to the Amazon authoritative server. So this is a step-by-step usually happens. We have our root servers based on the domain that we are requesting. It gets classified to other DNS servers. Then from that, it gets sent back with the actual IP address, as we've seen here for Amazon. So at the very top that we said that we have the hierarchy, which is the root name servers, and you can think of the official contact of last resort by the servers that cannot have a resolved name, and they are very important. So and to give you a visualization here of globally and worldwide, we have is that there are 13 logical root servers. Each of these servers is actually replicated many times across the world for any casting, because as we said, having one DNS huge big server is not efficient, and it's going to be very hard to maintain with the traffic that comes. So we must simplify it. So here the color shading shows how many servers actually exist. Darker blues highlight how many darker blue means more servers are being deployed. And then you can see a stronger coverage here in North America, Europe, and part of Asia, while other regions like Africa, South Africa have fewer. So the deployment ensures a lot of things. It ensures scalability, fault tolerance, and global availability of DNS. More about TLD, the authoritative servers. We want to look more about TLDs, and we'll talk a little bit more about them. So the servers are responsible for handling all the domains that share a top level extension. They also include country code TLDS, like .c for China, and we have .fr for France, .uk for the United Kingdom, also .jp for Japan. So that also helps us structure it down to country. And beneath the TLD servers, we have the authoritative DNS servers, and they're used to store the actual mappings of the host names and IPs back to the organization name. So these workflows looks like this. The TADL, what it does is basically direct queries from the given domain to the correct authoritative server, and the server provides that to the final IP address. And we have an example here coming up in a little bit of how that works. Also, in terms of global, we also have local DNS servers, and these rely on the local DNS name servers. So they do not belong to the DNS hierarchy. They play an important supporting role. So that when every internet service provider that we have, whether it's like residential, corporate, university, it has a local DNS server. This is often referred to the default name server. And on Mac, you can see it with the command, that specific command. On Windows, you can see it with ipconfig/all. So when a host makes a DNS query, what would happen is that it usually sends it to its local server first. The local server also maintains a cache of the recently requested mappings. So if it's already in the cache, it can be returned approximately. So it's the same idea of web caches. We have a local DNS server, and it can remember a lot of mappings, such that when we do request a DNS for a specific address, for example, if it is stored on the local DNS server, then it is sent back. So this mechanism also reduces DNS traffic and improves performance for end users. Okay, here we have an example. We have a host, engineering.ny.edu, and they want the IP for University of Massachusetts. So the first thing they do is, in step one, we request the host, the requesting host first, it queries the local DNS server, right? And then step 2 to 3 we have here. Then with the DNS, the local DNS server says, hey, I don't know I do not know the answer. I don't have the answer. So it queries the root DNS server, right? And the DNS server says, hey, I also don't know the IP address, and access the TDL server. The local DNS server then contacts the .edu TLD server that we have here, and it also sends a reply back to them saying, hey, I don't know the IP directly. You should contact the authoritative DNS server for the IP address. Then we have 6 and 7. The local DNS server would go back and contact the authoritative DNS server for University of Massachusetts here, right? And the authoritative server, which is like the host, or you can say kind of like the manager of the DNS, or the local DNS, would reply back and give the actual IP. And then in step 8, it goes back to the requester, which is engineering.ny.edu. So this is called an iterated query, such that we go through along the way, and we get a lot of replies saying that I don't know the answer, but here you should try this next. We also have another way, which is called the recursive query. And basically the same idea, same example. We want to just look at another approach, the recursive approach. So in step 1, what would happen is that the host would send the query to the local DNS server, and then the DNS server asks the root DNS server for help in step 2. Instead of just giving a referral, the root server takes responsibility and says, hey, I will go directly and query the .tld server itself. What happens at the TDL server is that if it doesn't know the IP, it directly queries the authoritative server directly without going back to the local DNS server. The authoritative server would reply with the IP address, because we know the every host would have an authoritative DNS server that are responsible, and they do supply us with the IP address. So when it does get supplied, and here in step 6, it would go back to the chain from the authoritative server to the TLD server, and then back to the root DNS server, and finally back to the local server that we do have. And then finally what happens is the answer is passed up back back to the host. And notice here that we have a recursive approach, and each server along the chain does the task of contacting contacting the next one until they go to the authoritative. So the authoritative is the last resort. The requesting host is the initial step. The second step is always the local DNS server. And just recursive is every server is responsible of contacting the next one. The other approach we looked at, the iterated one, is it contacts back the local DNS server and tells it, hey, I don't have it. Then they are responsible of contacting the next server. So this puts more load on the upper level servers, especially on the root and TLD server, since they carry the burden of the resolution, right? And that is it for SMTP and DNS. We said that the application layer supports user-facing services like email and DNS. SMTP enables reliable push-based transfer, and that is usually the IMAP between the mails and server. We use the SMTP to send and store. Those protocols that we see up there, IMP, POP, and HTTP, they provide flexible retrieval of management of messages as well. We talked about DNS, provides a scalable distributed solution for mapping the IP addresses that we saw with the way of hierarchy. So all these together, they highlight how the application layer underpins core internet services. So that is the idea of SMTP and DNS. So we're almost about end time. That is basically it for our lecture today. And if you do have any questions regarding the assignment, please don't hesitate to reach out. Also via office hours. And that is it. If you don't have any questions, then you have a good one, and I'll see you guys on Monday. All right, have a good one.